Okay, least squares. Who knows, who's seen these words in that order? No, excellent. Yeah? Okay. Okay, you've done lines of best fit before with Excel? You've done this every time, okay? This is what you've been doing every time you've done that. Okay, you've had data, you've plotted the data, okay, and then you told Excel find me a line of best fit, okay? Or long ago, someone just told you to just draw a line of best fit, and that was it. And I'm guessing you've seen this multiple times already, and you'll see it a lot in the future, okay? Every time you have a relationship that seems like it could be well modeled by a linear function, this is what you do. You plot the points, or you think about the points, and then you come up with a line that best fits them, okay? Now, what does best fit even mean, okay? You can't just eyeball the thing, because that's not a terribly rigorous thing to do. So what is the computer doing? Okay, so suppose you've got some points. Now here's the issue. With 2 points, it's easy. With 2 points, you just join them and there's your line, okay? With a lot of points, what the heck are you doing? You want to draw a line that best fits them, okay? Now a reasonable idea of best fit is the line's got to be close to the points, okay? Close to the points, those are the distances. Okay, you know, don't write this down. Okay? Incidentally, an upcoming project is sort of about this, okay? It's a simple version of this problem. Okay. What I tell you now will not help you at all. Yeah. Okay? So, you want the line to be close to the points. You want these distances to be as small as possible. Okay? So, how can you sort of come up with one number that represents all of that badness? Okay? The total badness you can think of, okay, add up all the distances. Okay. That turns out to be hard to deal with. So instead of that, we go, okay, add up the squares of the distances. Okay? So we say the sum of squared errors, which is what you'll see in the project, is equal to sum of the squared errors. Okay? So you add up the squares of all these distances, and you want to make that as small as possible. You want to make those points as close to the line as possible. Okay? And this line is y equals mx plus b. Okay, again, you've got all these points, and your job is to pick m and b, or the computer's job is to pick m and b so that this line is as close to those points as possible. Or in other words, those distances are as small as possible, or in other words, this thing is as small as possible. Okay, and that's optimization. Okay, so pick m and b so that this thing is as small as possible, and that's what the computer's doing. Okay. Now notice we're picking m and b. We don't do stuff like that in this course, okay? In this course, you've got one input, you tune it, and then you get the best possible output. Here you've got 2 inputs. So instead of having this kind of minimization thing, where you just change your input until you find the best output, you've got a surface, okay? In 3 dimensions, and you're trying to find the valley there, okay? And that's what this thing does. Okay, it finds the best m and b. Okay, and that's not that hard to do. You just, set derivatives equal to 0, and that'll do it. Okay, there's a nice expression for this. You can find m and b in terms of the data points. Everything's good. Okay. As I may have mentioned, I lost all my data this summer, so these are just pictures of my graded lab reports. So there's a line. Okay, what is this? This is enzymatic rate versus concentration of enzyme, which is something you guys may be seeing at the moment. I'm not sure. Okay, this is from biochem. Again, linear relationship, you find a regression line, okay? There's lots of other things like this, right? When you're doing gel electrophoresis, when you're doing column chromatography, when you're doing assays and you want to find out how much glucose there is by measuring the color of something, all those things you wind up drawing lines. Now you might say, well, why do I care? Okay, here's the thing. So maybe you're curious as to what people did before computers existed. Okay, so when people were finding trajectories in space, they did this kind of thing. Okay, they did least squares by hand. You may be thinking, what is the computer doing? And the reason that matters is that the computer might not be doing what you think it's doing. Okay? I don't want to say any more on that. So let's just say this. Sometimes if you're fitting a curve to something, you want to know just what curve the computer is fitting in what way, and I think that's important. The other reason that matters is this. Okay? In biochem, you'll see stuff like this. Okay? These are called Michaelis-Menten curves. Okay? That's velocity of an enzymatic reaction, and that's presence of substrate, the fuel for the reaction, essentially. Okay? And you get data points that fit those curves. And yes, I'm so proud of the check marks. Okay? You want to fit those curves to those points. Okay? what do you do? The computer doesn't have in it that hyperbolic model, okay? It has lines, it has quadratics, it has this kind of stuff. It doesn't have hyperbolic models. So if you want to fit something like that to your data, what do? You can't just ask the computer to do it because the computer doesn't have that model, okay? So what you essentially wind up doing, if you're using Excel, is you tell it, minimize the sum of those squares, okay? And it can do that, okay? So it matters for people to understand this, and literally in biochem, unless she's changed the thing, you'll be doing that.